One feature we wanted to include in the BlueSky electricity model was a nonlinear element. Generally, as more capacity is built of a technology, the less expensive the capital cost becomes. We call this learning. Learning is a nonlinear function, which makes it difficult to model. We have implemented several options for examining capacity cost changes due to technological learning in the BlueSky model. So we have 3 options within BlueSky. We have exogenous learning, which basically means that we set the capital cost as an input and it remains independent from the capacity that's built in the model. The second option is to have iterative linear learning. This allows the model to remain linear optimization, but we still see feedback between the amount of capacity built and capital cost. Next, we have the nonlinear learning option. So here we embed a nonlinear equation in the optimization problem. Now let's take a look at where in the code we have these different settings. So if you look in the BlueSky folder, in SRC, models, electricity, and then scripts, and open the electricity model.py file, and taking a look at the objective function section, we'll look at where it lists the switch. This section is if we have nonlinear expansion costs. So this is what the capacity expansion cost expression looks like for the nonlinear version. As you can see, it is a function of capacity builds, and it's also nonlinear. And then this is the expression for the capacity expansion cost for the linear version. Now, this is applied for both the iterative version and the exogenous version. But in the iterative linear version, we update the cap cost learning with each iteration. So to look at the iterative updates, we'll jump to a different file in SRC integrator and then Gauss-Seidel.py. In this section, if we have the electricity model running, we're going to run the electricity model. And then after that, if we have the learning switch set to 1, which means we're running an iterative linear run, then we update the old capacity, set the new equal to the old capacity, and update the cost based on the new capacity. And then if the run is not converged, then we iterate again. More information can also be found on the README under the electricity model of the BlueSky repo. It explains the learning switch a bit. You can see more about how the objective function is implemented depending on the switch. If you open the model runner, select GS combo. For now, we'll only have the electricity model running for simplicity. I'm also going to lower the tolerance of convergence a bit. I've already changed the years so that only 2030, 2040, and 2050 run, and only selected one region, region 7. So in order to change the learning switch, this is the switch you would change. For exogenous learning, we want to leave that as a 0. So I'll save those changes and hit run. For linear iterative learning, we leave all the same settings, but change the learning switch to a 1, save those changes, and run that as well. For the nonlinear learning setting, we want to change the switch to a 2, save those changes, and do another run. Now I've already renamed all of the runs. So we have the exogenous run, the linear iterative run, and the nonlinear run here. And now we'll take a look at some of the build results. So I'll open up the model viewer, select all of the runs, select region 7, going to the capacity tab, and we'll examine the differences in the builds. So here we have mostly the same amount of capacity built over all of the years. The only difference here is the onshore wind capacity is a little different, and steam. So these two runs have virtually the same results in terms of capacity builds, but it is slightly different than the exogenous results. So I'll focus in on wind capacity because that's the biggest difference here. I already pulled this data from the output directory of all of these runs. So pulling from various parameters like cap cost learning, it does depend on which run you have. It may be in the parameters or you might have to calculate it yourself, but I essentially extracted what the results would be from all these runs. For the exogenous learning run, we see a steady decrease in capital cost of wind over the years. For iterative linear learning, We see a steep drop in the capital cost of wind between 2030 and 2040. That's because in 2030, there's a significant amount of wind capacity being built. In the nonlinear learning case, we also see a similar drop-off from 2030 to 2040 of the capital cost of wind because it's building the same amount of capacity in the same timeline. I'll note that for these examples, the linear problems are solved using the HISE solver and the nonlinear run uses the IP-opt solver. As you can see, there's a big difference in runtime between all three runs, the nonlinear run being significantly slower. The iterative linear learning solves with one additional iteration, and we see similar results between the iterative linear learning and nonlinear learning run. As a reminder, these runs are all only using the electricity module. These methods become more complex when other modules are included in the run, and we may need more iterations to settle on a solution.